In this tutorial, I'm going to show you how to establish SPI communication with the DS3234 real-time clock. The purpose of this tutorial isn't to quickly show you how to get your SPI clock up and running. Instead, I'm going to show you something better, how to read a datasheet and use the native SPI functions included with Arduino to access the clock. This will allow you to use any SPI device and not be bound to the availability of pre-existing libraries and tutorials. Now, don't get me wrong, libraries and tutorials are great and make the Arduino an accessible platform to beginners. This is part of the reason why Arduino is so popular. However, I feel many people are constrained in their ability to accomplish their goals due to reliance on libraries and tutorials. I used to rely on libraries and tutorials. I found some libraries just don't work. I found some libraries don't give me the functionality I need out of the device. I have found errors or skipped steps in people's tutorials that have led me to great frustration. By understanding how to read the datasheet and how to use the Arduino's commands to access SPI communication, you no longer rely on anyone other than yourself. This enables you to troubleshoot your problems and allows you access to any SPI device that you want. And this is what I'm trying to show you in this tutorial, how to start talking to a chip from scratch without help from anyone else. What you're going to need to be able to complete this tutorial is an Arduino Uno, a DS3234 breakout board, a breadboard, a cable to bring the computer to your Arduino, and some wires to bring it all together. Before we go ahead and connect the clock to our Arduino, we should consult the datasheet and make sure that the clock is compatible with the Arduino. Not knowing anything, the datasheet would be able to clarify for us. Taking a look at the datasheet here, I have it saved to my desktop. If you don't have a copy of this datasheet, check the description for more details. On page 1, we see the typical operating circuit that is supposed to surround the clock. Any well-designed breakout board would include this circuit such that you can interface the breakout board with your microcontroller unit. In this circuit we see quite a few pins, and on our DS3234 breakout board we also see some pins. We see ground, VCC, SQW, and then the SPI lines, clock, master input, slave output, master output, slave input, and chip select. I think it's pretty safe we can assume that the pinout of the breakout board matches that of the datasheet. Before we hook the chip up to our Arduino, we need to make sure that the chip is compatible with our Arduino. Going down to page 2, we see the recommended operating conditions, and we see that it recommends a supply voltage connected to VCC between 2 and 5.5 volts. Knowing that the Arduino is a 5-volt system, a 5-volt device, we know that we're not going to do any damage to our IC by connecting it to the Arduino. To wire this up, we're going to want to connect VCC to 5 volts ground to ground. Connect CLK to the Arduino SPI clock line, represented by the letters SCK in this pinout. That is CLK to digital 13. Connect MISO to digital 12. Connect MOSI to digital 11. SQW is an interrupt output pin, so we'll need to connect that to an interrupt. I'll be using interrupt 0 found on digital 2. Finally, connect your chip select pin to any available digital output. I am connecting CS to digital 8. Let's go ahead and wire this all up. The next thing we're going to want to do is open up the Arduino IDE. Before we start any coding, we should lay out what it is we want to accomplish with our real-time clock. Real-time clocks offer a variety of features, and in the interest of keeping this tutorial short, I'm going to list 3 things that I want to accomplish in this tutorial that can be done with this real-time clock. The first thing I want to do is set up the clock such that we get a SQW output. So real-time clocks often offer this feature, and the DS3234 does, where we can get a standard output from the clock, a frequency output, that we can use to keep track of time. If we scroll down to page 14 of the datasheet, we can see that we get a square wave output frequency ranging between 1 Hz and 8.192 kHz. So what this means is we can get these pulses out, and we know that, for example, we can keep time accurate to 1/8192th of a second. So I want to set up our clock such that we can actually control the frequency output, allowing us to do accurate timekeeping later if we needed it. The next thing I want to do is be able to set the time of the clock. It's a clock, so we want to keep track of time, right? And then the third thing we want to do is read the time of the clock. So 3 discrete objectives that we're going to complete in this tutorial using the DS3234. Now, as I mentioned earlier, there is no address for a SPI device. Instead, we have a chip select pin, and we can assign that on our end. So, for example, in our circuit, we have the chip select connected to digital 8. So I'm going to write that down now. I'm going to create a value here called chip select, and I'm going to say it is equal to 8. So this is effectively our address, our method of talking to this particular chip. The next thing we need to know are the registers of the chip relevant to what it is that we want to accomplish, and this is also held in the datasheet. The first thing we want to do is set up the clock such that we get a square wave output. Well, if we scroll down to page 14 on the datasheet, this is where we can see our square wave output frequency as well as some other bits that we can control in the control register. Now you'll notice that there are two addresses here in hexadecimal format. One is to read the chip, so if we want to read something from the register, it has one address that we need to talk to, and if we want to write to the chip, that's a different register that we need to talk to. So I'm going to write both of these down in the sketch. The first one will be write control reg, and that one will be equal to 0x8e. The next one we're going to want to write down is the read control reg, and that is 0x0e. The other registers we're concerned about are the ones that are going to be relevant to setting the time of the clock and reading the time of the clock. As I mentioned, we have two different registers for this, and so we need to be aware of what both of them are. If we scroll up to page 12, we see the address map for the DS3234 timekeeping registers. And we see that there's the address read addresses listed in the left column here, and the write addresses listed on the right. We're going to be writing down the address for the seconds register, and then we can increment by 1. As we see, it always increments by 1 here all the way up to year. So let's write down this timekeeping register. First, I'm going to write the write time register, and we know that that is 0x80. And then we're going to write down the read time register, and we know that's 0x00. Alright, so let's start coding. The first function we're going to create is going to be called RTC, standing for real-time clock init, which is our initialization function of the RTC. We're going to receive two parameters in here. We're going to receive our chip select pin, and we're going to receive our interrupt frequency that we want. Now again, if we scroll down to page 14, we see our square wave output frequencies range from 1 Hz to 1000 Hz, 4000 Hz, and 8000 Hz approximately. So I'm just going to write down what these options are. So here we have it. We're going to define it for ourselves such that we have 5 options. Option 1 is where we get a 1 Hz pulse versus 2 at 1000 Hz pulse, all the way down to 4 8000 Hz pulse. And finally, option 5 is off so that we don't get any square wave input. So the first thing we're going to want to do is talk to the chip, or tell the chip that we want to talk to it. So to do that, we need to control our chip select pin, and to do that, we need to set up our chip select pin using the command pin mode. So we're going to set up chip select to be an output. The next thing we're going to do is initialize communication with the DS3234 using the command digital write. We're going to set our chip select pin to be low. And if we're going to do that, we're going to have to eventually stop communication by using the command digital write chip select high. Now in between here is where we actually talk to the device. So to be able to talk to the device, we need to use the command SPI.transfer. And you go, where is this from? Well, we need to import a library here where we go to Tool, go to Sketch, include library, and then SPI. And by importing this library, it unlocks a bunch of functions for us, including SPI.transfer that I have down here, where we can communicate with the chip. So if we're going to talk to the chip, we set the chip select pin low. We then transfer it to it what register we want to talk to. I don't know, I can't tell you right now what the state of the control register is in. Here we have an example with some zeros and some ones in it, and you might have programmed a particular timer in here, like an alarm in it, in bits 0 and 1. That's what these allow you to do. Or you might have configured it to be a certain way, and we don't want to just completely demolish the control register here and write a new register. Instead, what we want to do is flip the bits that are relevant to the objective that we want to achieve. So if we read the datasheet here, we see that the BBSQW is when set to logic 1 with int cn equals 0, this bit enables the square wave. Well, we want to do that, so we want to be able to set bit 6 to be a logic 1. As well, we want to set int cn, which is bit 2, to be a logic 0. So we want to control bit 6 and we want to control bit 2. As well, we're going to want to set our interrupt frequency, which are controlled by the rate select bits, which are bits 3 and 4, which allow us to set the square wave output frequency. So we don't want to change bit 7, we don't want to change bit 5, or bits 0 and 1, just 2, 3, 4, and 6. So how do we do this? Well, we need to read from the chip what the current control register configuration is. So we're going to SPI transfer, we're going to tell it what register we want to talk to. We want to talk to the read control register, and then we want to actually save that value. And that is done by creating a value. It's going to be just a single byte value, and I'm going to call it original config. So the original configuration, and that is equal to SPI.transfer again, 0x00. Why 0x00? That shows that we want to read from it, and we want to read from it from the last register that we talked to. So we say, hey, we want to talk to the read control register, and now we want to receive something from it, from the read control register. So now we have this value called original config, we have the data that we want, and now we can stop talking to the chip by setting our chip select to be high again. Now I'm just going to add a 10 millisecond delay here, just in case the Arduino moves too quickly relative to the chip. So now we have the original configuration of the control register from the chip, and we want to modify this configuration to serve our needs, whatever they are. So I'm going to create two new values here. Both of them are going to be bytes. The first one is going to be called config modifier, and the next one is going to be called new config. So the idea here is we have our original configuration. We're going to modify that configuration to create a new configuration which we write back to the chip. So the first thing we're going to want to do is evaluate if our interrupt frequency option that we sent into this function is equal to 5. Because if it is, that means that we want to turn the square wave off. So if it's equal to 5, we want to set this bit 6 to be low, because if it's low, then we can't get the square wave out. So we're going to say our config modifier is equal to 0b10111111. So there are 8 bits in this byte. Here the cursor currently marks the halfway point. So what's happening here is everything is a 1 except for bit 6, which we are going to make 0. Why? Because now we can create our new config, and our new config is going to be equal to the config modifier and this is bitwise operator and the original config. So what's happening here with the bitwise operation is we're saying whatever the bit configuration is before, and these values produces our new config. And what the and means is if bit 0 in our original config is 1, because bit 0 in our config modifier is also 1, that means that our new value in new config, bit 0, is also going to be 1. If I had set this to 0, it doesn't matter what is happening in original config, bit 0 is going to be a 0. So what I'm effectively doing here is forcing bit 6 to be 0 regardless of what the original configuration is, and otherwise we're preserving the rest of the values if they happen to be 1, and if they happen to be 0, then they stay 0. So that's our new configuration. The other option is that we don't have the square wave off, but instead our interrupt frequency option falls between options 1 through 4 here. Now on the data sheet, we see that in binary here, we don't actually have options 1 through 4, we have options 0 through 3. So we're going to have to modify that in just a moment. So if it's not interrupt frequency equals 5, then it's going to be int frec is less than 5. in which case we're going to have to create a new value here called our frequency option, and it's going to be equal to our int_freq that we gave into the function here, -1. And that way it matches up with what the actual square wave output frequency options are. Now, for us to have a square wave output, we need to make sure that, according to the instructions here, bit 6 is a logic 1, and bit 2 is a logic 0, and bits 3 and 4 reflect the frequency output that we want. So we're going to create our config modifier here. And the first thing we're going to do is take our frequency option, so this is a value between 0 and 3 now, and we're going to shift it over 3 places. Why are we doing that? Sorry, I should put in equals here. Why are we doing that? Well, because our frequency option could be value 0 through 3. Let's say it's 3. If it's 3, that means bits 0 and 1 are populated. Well, bits 0 and 1 on the control register point to alarm 2 interrupt enable and alarm 1 interrupt enable. They're not relevant. So what we need to do is move those 2 bits over to the bit 3 and 4 position, and you do that using this bitwise operator, which allows us to move it over 3 positions. So we're moving it over 3 positions, and then we're going to say OR, and then we're going to put in the byte value 0100 0000. So again, my cursor here is marking the halfway point. What we're saying here is everything is 0 except for bit 6. What the OR operator does is it says if either the value in here in this byte, if any of the bits in this byte are 1, and if any of the bits in this byte are 1, make it equal to 1 here. So in this case, we have shifted over our option to bits 3 and bits 4, and we have made it such that bit 6 is for sure going to be high. Note bit 2 is going to be low here, and bit 2 is going to be low here, which is the other requirement that we need to meet. So then our new config, this is the configuration that we're going to send over, is going to be a combination of our config modifier, or, and we're going to have to do some manipulations on our original modifier, original config, I should say, and combined it with an AND of the value 0B111000011. So what this does is, here my cursor now, here, let's add that there. My cursor now marks the halfway point. We see that we are for sure making sure that bits 2, 3, and 4 are low when combined with the original config. Otherwise, we preserve the rest of the data. So bits 2, 3, and 4 are low, and then we are ORing it with our config modifier, in which case we want bit 2 to be low, and then we want bits 3 and 4 to reflect what our option is, be it options 0 through 3 on the square wave output frequency chart. So what we're going to get here is a value where we maintain bits 0, 1, 5, and 7 are going to be preserved in the original configuration, and otherwise we're going to have bit 6 bit 6 high, bit 2 low, and bits 3 and 4 reflect what our frequency choice is. So now we have our configuration that we want to write to the chip. So the first thing we do is digital write. We're going to digital write our chip select to be low so that we establish that we want to talk to it, and I like to make it high after or in the code so that I don't forget to set it high again later. We're then going to, using the command SPI.transfer, we're going to talk to the write control register, and then we're going to have to send over what data we want to write to that register, and that data is our new configuration. At the end of this, just add a delay for 10 milliseconds. Oh, and give it a save. Let's give it a save. So I'm going to save this to my desktop, Arduino sketches. I believe this is tutorial. This is going to be tutorial 9. I'm going to call it tutorial 9. So right, there you have it. Now we can initialize our real-time clock and set what frequency we want out of the square wave output of the clock. So that means we have met requirement 1. Now the next thing we want to do is set the time of the clock and then finally read the time of the clock. So using the datasheet, let's go back up to page 12 here where it shows the address map for the DS3234 timekeeping registers. Now similar to the DS3231, which I covered in my I2C communication tutorial, we see that we have binary coded decimal formats for keeping track of our time. That is, bits 0 through 3 represent individual seconds, and bits 4 through 6 represent groupings, represent 10-second pairs, sets. I don't know what you want to call it. The point is this isn't standard like counting from 0 up to 60 in bits. It is a more complicated way of keeping track of a value, I would say. It's less intuitive to us. And so we need a way to convert this binary coded decimal into a value that represents a decimal to us so that we can, when we say 59, it actually means 59 seconds. So we're going to have to create two functions that do this conversion for us. And the reason why we need two is so that we can write to the chip and we can read from the chip. So the first one we're going to create is going to return us a single byte value, and we're going to call it convert value in. And into it we need to pass a single byte value, which I will call value. And the code for this is uint8_t converted val is equal to value minus 6 times value shifted over 4. So this is the formula I used in the earlier tutorial that allows you to convert it, and then we're just going to return out of it converted val. Similarly, we're going to need for values out, convert value out, and again we're going to receive the same 1 byte value, and the formula for this is converted val is equal to value plus 6 multiplied by that value divided by 10. And then we are going to return our converted val. So now we have these two functions to convert our binary coded decimal into standard decimal that you and I would understand. So objective 2 is to set the time of the clock. To do that, we're going to create a new function, and it's going to be called void set time. And into it we're going to pass our chip select, and then we're going to have to pass in a structure that is going to hold our values for our clock. So I haven't created it yet, and I'll do it in just a moment. I'm going to call that structure time parameters, just like I did in the earlier tutorial, and it's going to be called time vals locally. Okay, so let's create this structure. I'll create it up here at the top. To create the structure, it's going to be a type definition of a struct called time parameters. And in it, we're going to have, everything's going to be a single byte. We're going to have our seconds, we're going to have our minutes, and I'm just going to copy paste this to make it a little bit faster. We're going to have our hours, day of the week, date, month, and year. So we have our minutes, we have our hours, we have our day of the week, we have our date, we have our month, and we have our year. And notice how it's following the same order as it says here on page 12 of the datasheet. We have seconds, minutes, hours, day, date, month, and year. That's how I know that I can store these values in the clock, and it's in the same order as what the clock can keep track of. So we're going to receive in our structure called time vals here, and we're going to be setting the time, which means we're going to want to talk to the write register. So the first thing we need to do is we're going to set our pin mode of our chip select to be an output, and then we're going to write our chip select to be low, and then we're going to write the chip select to be high so we don't forget. And then we're going to transfer through SPI what register we want to talk to, and since we're setting the time, we're going to want to talk to the write time register, and then we're going to send the value that we want to write. So use SPI.transfer again, And the value we want to write is the converted value using our convert value out function here. We want to send to the chip time valves pointing to seconds because we know that that is the first value at hexadecimal 80 here. Now, we could stop here. We could write this block again, copy, paste, and increment the right time register by 1, and then replace seconds with minutes so that we're pointing to hexadecimal 81 instead of hexadecimal 80. But we can also use a little cheat here. We're just going to copy SPI transfer, and we're going to paste it for minutes, hours, day, date, month, and year. And then all we have to do is change the endings here. So that's for minutes, that's for hours, that's for day, that's for date, M for month, and Y for year. And then we can digital write the chip select to be high, and then as usual, we're going to add a quick little 10 millisecond delay here to the end. So there you have it. That's all that's needed to be able to set the time of the clock here. We're just going to say, hey, we're going to talk to register 80, and then we're going to send the data, and then it automatically knows to advance forward to the next register, and then we send the minutes. And we continue along until we have sent the year, and then we set the chip select pin high, which means that we've stopped talking to it, and then we give it a bit of wait, and now the clock saves the date to that register, to those registers. So now we've been able to set the time. The next thing we want to do is be able to read the time. So we're going to have to create another function here, so void read time. And into it, we're going to pass the chip select pin, and then our time parameter structure, which I'm again going to call it time valves locally. And just like before, we're going to have to set the pin mode of our chip select to be an output. And keep in mind, you don't actually have to do this in every function. You could do it in your setup and then skip this line, but there's also a chance that maybe you didn't do this in the setup, or maybe the chip that you have, like you're talking to a new chip for the very first time. It doesn't really hurt putting this line of code in every time, even though it seems a little redundant. We're going to digital write our chip select to be low to be able to talk to the chip, and we're also going to have to set it high at the end. And then since we're here, let's just add that 10 millisecond delay at the end. And now we're going to want to read the time. Well, this shouldn't come as much of a surprise. To do that, we use the command SPI.transfer, and we're going to send the read time register that we defined earlier. Now we want to read time. Well, how do we do that? How do we save that? Well, we're going to want to, because we're reading the time register which we wrote is 0x00, we know that that's our seconds register, and then it's going to increment through down to year register. So we're going to say that our time valves second value is going to be equal to convert the value in, because binary coded decimal, convert the value in SPI.transfer, and just like before, when we are reading, we want to have 0x00 being transferred, and there you have it. So now we have written the seconds value from the clock. And again, we can use that little cheat where we copy this, and we're just going to paste it for minutes, hours, day, date, month, and year. And all we have to do is change it to the correct value in our time parameter structure. So seconds, minutes, hours, day, date, month, and year. We do that, we then set the pin to be high so we stop talking to the chip, and then we just add a quick 10 millisecond delay. And that's all there is to it. So now we have written a function to achieve objectives 1, where we get a square wave output, objective 2, where we set the time of the clock, and objective 3, where we read the time of the clock. We have our chip select pin defined up here, and this isn't exactly the best way to do it, but it's here, so I'll just leave it there. I'm also going to define our interrupt frequency that we want. So this is, do we want 1 hertz, 1000 hertz, 4000, 8000 hertz? I'm going to go with the ultimate speed, 8192 hertz frequency output of the clock. So I'm going to set that equal to 4. All right, so now we can scroll down to our void setup, and in void setup, we're going to begin our SPI communication. We can also set up some parameters here as to how we want to talk. So the first thing we want to do is set the bit order. And we're going to use the option MSB first, which means most significant bit first versus least significant bit first. And most devices that you're going to talk to communicate in the order of most significant bit first. Now, how do I know that it's most significant bit first? Well, checking the datasheet. Let's scroll down to page, well, actually, the real easy way to do it is just do a Control F on most significant, and we see that on page 18 here, we have address and data bytes are shifted most significant byte first into the serial data input. So that's how we know that we want MSB first versus least significant. And if we do a search on least significant, nothing shows up. So that's how we know that it is definitely a most significant bit first chip. And then the next thing we're going to want is the command SPI dot set data mode SPI underscore mode 1. And what this does is it sets the SPI data mode, or the clock polarity and phase of our clock pin. So in SPI communication, we have our clock signal that's constantly pulsing, and we send data relative to that, and that's what SPI mode 1 allows us to do here. Next, we're going to set up an instance of serial communication, so serial.begin with a baud rate of 9600, and this is just so we can get a print output of what's going on, and then I'm going to give it a 10 millisecond delay because I like doing that, it would appear. Next, we're going to initialize our clock using the function we created called RTC_init, and remember we need to send into it our chip select pin as well as our int frequency option. Then we're going to want to set the time, and we're going to do that, and when we set the time we need to pass in two values, our chip select, and then we need to pass in some values that keep track of time. So I'm going to create a structure here called example vals, and I'll do that right above the setup here. So we're going to create a time parameters structure called example vals, and it's going to be equal to 50, 59, oh wait, so 50, 59, 23, 1, and I don't know if that's actually right, 31, 12, and 10. So remember, this is seconds, minutes, hours, day of the week, date, month, year. So you can see that I'm saying this is Monday, December 31st, 2010, 10 seconds to midnight. So this way we can see the new year rolling. So there's a structure of example values that we can use to set the time. This would be whatever time you want to have set, so you could program this according to the real time of the day that it is. So we've set the time, and then the last thing we're going to want to do is attach an interrupt to the 0th interrupt on the Arduino. We're going to, when that interrupt happens, we're going to point it to a function called timefunc, which we have not written yet, and we're going to be looking for a rising edge. So I mentioned we haven't written the timefunc function yet, and what we're going to need to do is create a value here called time trigs. So this is how many triggers of the clock have we received. It's going to be starting off equal to 0, and then we're going to create a function here called timefunc. And in timefunc, we're going to say time trigs plus equals 1 to increment it by 1. So every time we get the pulse on our interrupt, using the interrupt, we advance time trigs counter by 1, and we can use that to keep track of time accurate to the frequency of that pulse. So now we've configured the clock, and the next thing we're going to do is drop down into our loop here. I'm just going to add some space here to bring it up. We're going to drop down into our loop. The first thing we're going to do is we're going to wait for 1 second. Then we're going to read the time of our clock. So to read the time, we have to pass in the two values, our chip select pin, and then we're going to pass in, I'm going to use the same structure called example vals to keep track of what the time is. So we initialized it, and now we're going to update it. Then all we have to do is print out what those values are. So I'm going to print out time, and I'm going to print example vals, and it's going to be hours first, followed by the printing of a colon. And now I can copy this for minutes and seconds, get rid of that last colon there. Our second value will be our minutes, the last value will be our seconds. And instead of just printing it, we're going to print line that so that it writes it all on one line. Then we're going to do the same thing for the date. So our date is going to be serial.print example vals.d, and then we're going to print a slash, or actually instead of d, let's call it year. So it's going to go year, month, day. So year, month, and then day. Get rid of the last slash, and we're going to make that last line a print line. So what we're going to do is get time in the format of hours, minutes, seconds, followed by date in format of year, month, day. And then finally, the last thing we want to keep track of is our time triggers. And that will just be a print line of our time trigs value. And then we're going to reset our time trigs to be equal to 0. Give this a save and upload it to your Arduino Uno. And make sure that you correct all the missing semicolons that you're inevitably going to have. Or a else if statement here instead of just else. Remember to add your semicolons at the end of your structures, and now we are error free. So that's not too bad. We're going to upload it to the Arduino, and then we're going to open up our serial monitor by clicking on Tools, and we're going to go to Serial Monitor. And here we have it. So we see our clock is advancing. It is 53 seconds, 54. I'm just going to give it a minute here so we can ring in the new year. And we see our time triggers here is 8,287-ish, 85-ish. Oh, and Happy New Year, by the way. So we saw that the clock, I'm going to stop the auto scroll here. We saw that the clock rolled over to the brand new year right here. Going back to the auto scroll, we see that we have our time triggers here, 8,285. Note, it's always going to be longer than the frequency of 8,192 Hertz, and the reason for that is because we're waiting for presumably a full second, and then we're doing a bunch of things, and then we're posting our time triggers and resetting it. So more time is being spent, like we are spending time actually printing these statements, so you should always expect your time triggers to be higher than the interrupt frequency that you set. For more accurate timekeeping in your program, though, you could actually use these time triggers. Instead of the delay function here, you could just say, do it after 8,192 time triggers have happened, and then you reset your time triggers and do the code that you want. So it would allow you for more precise timing that way. So there you have it, how to set up a DS3234 on your Arduino without the need of somebody else's library, allowing you to configure your clock however you want it using the datasheet. I hope you enjoyed this tutorial. For more tutorials like this, visit thezanshow.com.